This is where we left off. And I gave you an example problem, and the example problem said, what product is obtained from the reaction of each of the following alcohols with ABC? All right, so A was chromic acid, B was the HOCl, which is aka bleach, or hypochlorite ion, and C are the reagents required for the Swern oxidation. So they didn't even bother writing the reagents, they just gave you the name of the reaction, Swern. And you're supposed to know what goes on and what kind of product is formed from these reactions. Okay, so molecules. 1, 2, 3, 4, 5, 6. So that means part A will have 6 answers, part B will have 6 answers, and part C will have 6 answers. 6 times 3 is 18. So this one little tiny example problem that I've spelled wrong up at the top of the slide is going to lead us to 18 different products that they want represented in this question. I love it. Okay, so let's go back and first remember, we've already did this, folks. 1, 2, 3, 4, 5, 6, we have already answered in a previous example problem when we used chromic acid. Go back and take a look at your notes if you don't believe me, but just in case you want to see that all over again, we're going to do them. And the reason is because these answers are going to be very common to some of the other ones that you're going to see in Part B and Part C. So let's first take our 3-pentanol. All right, so 3-pentanol, pent is 5. 1, 2, 3, 4, 5. It gives us a good review of anything, so it's okay. So 3-pentanol, 5 carbons in a row, in a chain. There they are. And on the third carbon, I'm going to have an OH group. That's why there's a 3 in front. So for part A, they want to know what is formed if you add H2CrO for chrome. Okay, so we know what chrome does. It's going to take a look at this H. There it goes. Then it's going to take a look at a neighbor H, and that carbon does have one. It's a secondary alcohol, so it has it. So, beep, off it goes. And we will form a double bond between the two. There you go. There's the quick review of Part 1A. Now, let's take a look at B. B says, what would happen if you added HOCl? So this is the hypochlorite version. All right, not a problem. Let's go back to the original. That's what we had. And what does hypochlorite do? It does the same thing. It looks at the H on the O and it goes bleep, off it goes. It looks at the hydrogen on the carbon, bleep, off it goes, and we get another double bond that forms. It's the same product. It's the same product. So this question's not as difficult as it might seem in the beginning. So what about C? The Swern reaction. Okay, so let's look at the difference here. There's my starting reagent. The Swern reagents come in, and beep, off it goes. The neighbor carbon, beep, off it goes. And a double bond forms in between them. Part A, Part B, Part C are all different reagents, and look at what has happened. It gives us the same darn product every single time that we do it. So this is going to turn out maybe a little bit easier than some of the others. All right, so let's take a look at number 2. Number 2 was a 1-pentanol. All right, so pent is 5. 1, 2, 3, 4, 5. On carbon number 1, I have an OH group. So I'll draw it like that. And we'll do the same thing. So for part A, we're going to add chrome. So that chrome's going to come in. Beep, off it goes. That neighbor carbon, that does have a hydrogen. There's actually 2 of them there. I'm going to draw one of them at least. The second one, beep, off it goes. And a double bond will form between that carbon and that O. And that gives us an aldehyde. In part 1, that was a ketone. This is a ketone up here. C double bond O in between two carbons. That's a ketone. Here we have a C double bond O, and we have a hydrogen on one side and a carbon on the other. This is at the end, so this is an aldehyde. However, without any interference from something like PCC, this is going to oxidize yet again. That's the thing with chromic acid for these ending OH groups. If it gives you an aldehyde, like this one did, then this chrome is going to go in and squeeze another oxygen in between that carbon and that hydrogen. So now we end up really here with a carboxylic acid. This is a two-stepper, and these are the things that you have to worry with when it concerns the primary alcohols that we use. So when primary alcohols oxidize, they will go to aldehydes, but they do not stop there, right? We've talked about this over and over. When they form aldehydes, unless you do something to them, they're going to oxidize again. And when they oxidize again, you end up with a carboxylic acid. Now, let's take a look at B. Now, this time I'm going to draw something different. 1, 2, 3, 4, 5, and we have this OH group that's up here. So maybe this didn't come across very clear when we began to lecture with these reactions. But for part B, when we use something like hypochlorite or bleach in acetic acid, when we use this type of reagent, same kind of thing happens in the first step. Beep, off it goes. The neighbor carbon, beep, off it goes. And we have that extra hydrogen that's here, and we have that double bond that just formed. So it is an alcohol. It is still at the end, and that ending alcohol on that carbon makes an aldehyde just like before. The difference, though, is that for part B, it will not oxidize again. It will stop here. Only the chromic acid will oxidize for a second time to make these carboxylic acids. So something like HOCl or bleach in acetic acid, that does not go forward for a second stepper. This is it. This is where we stop it. So this is a aldehyde product that gets formed, and this will be the major product for that reaction. Now let's take a look at Swern. Talk a look. No, let's take a look at Swern. What does the Swern do? Folks, let's go back. I'm going to erase this, and we're going to draw with our starting alcohol. So with the Swern reagents, the Swern reagent goes in, and guess what? Beep, off it goes. And then that neighbor carbon, beep, off it goes. And we end up with a double bond that forms there as well. As with the hypochlorite, the Swern does not go another step. It ends at the aldehyde yet again. So quite honestly, B and C are going to be identical. Really, every single time that you look at the reagents for B and you look at the reagents for C, they are going to be the same product in the end. They do the same thing. They oxidize the same way. They do not go forward and oxidize a second step. Only in part A do you get this aldehyde as product number 1, and then it furthers again and goes to the carboxylic acid. That is really the major difference between chromic acid and part B and part C. You can get this to stop, though, and make it match the others if you add the PCC version. So if I add PCC in part A, then all 3 of my products will be identical, because they will all stop at the very first step. So that's going to be the major thing that we have to watch out for number 3, number 4, and number 5. All right, so let's go on. Let's take a look at number 3. Number 3 was a 2-methyl 2-pentanol. All right, so 2-methyl 2-pentanol, pent 1, 2, 3, 4, 5, And on carbon 2, I have a methyl group, and on carbon 2, I have an OH group. So if I take a look at this alcohol, these reagents for our first one, chromic acid, does the same thing. It goes in, beep, off that hydrogen goes, it goes to the neighboring carbon, and beep, ew. Wait a minute. That carbon doesn't have a hydrogen. I can't beep it off. So this carbon to the left and the carbon up above and the carbon to the right, folks, there's no extra bond here that goes to a hydrogen for me to remove it. So if I go back and take a look at the basics, this alcohol is a tertiary alcohol. So that means it doesn't undergo oxidation at all. There's no oxidation for chromic. There's no oxidation for hypochlorite. There's no oxidation for the Swern. They all behave the same way. They have to beep the hydrogens off of there in order to form the double bond. And they all work the same way in the very first step. You can't do that here. There's no hydrogen on that carbon because it's tertiary. So no products. No products are going to happen because that alcohol cannot oxidize. Only primary and only secondaries can. All right, so let's take a look at number 4. Here we have a 2,4, and this is a hexane diol. So hex is 6, 1, 2, 3, 4, 5, 6. There they are. At carbon number 2 and at carbon number 4, there's diol. So di means 2. So there's 2 alcohol groups on this thing. Where are they? Carbon 2 and carbon 4. So here's an OH, and there's an OH. Okay, so for part A, with my chromic, H2CrO4, same deal, same concept. There's more than one OH, but we've already said that's okay. We can do these. We do these the same way. We're just going to have to add more beeps in. So beep, that hydrogen off, beep, that hydrogen off, that carbon, beep, that hydrogen off, that carbon, beep, that hydrogen off. So in every case, we get a double bond that forms there. These form ketones in both locations, so it cannot oxidize. Again, they're not primary, they're not at the end. Neither one of those carbons has a hydrogen on either side of it, so that's it. This is as far as it goes. So if we do B, and this is our hypochlorite, it oxidizes the same way, beep, beep, and double bonds form, and that is the same product that we get for hypochlorite. For C, we have the Swern. So the Swern's going to use different reagents. Remember, super, super cold there. The Swern's going to go in, beep, beep, those hydrogens off, just like before, and we form double bonds yet again in the same way. So all 3 of these reactions will give you the same product. And that product is right here. It's a dione. One is a ketone. Ketone ends in O-N-E. We don't know how to name this. We'll learn how to name these later, but we don't know how to name these right now. That's perfectly okay. I'm not asking you to, but we can at least draw the structures of what show up. All right, so the next one, number 5, was cyclohexanol. All right, so cyclohexanol is a ring structure, and this has an OH on it. Doesn't really matter where you put the OH. I don't care. I like to put it up at the top because I think that's an appropriate kind of starting place, just because that's how we read a clock in a way. But you can put it to the right. You can put it to the left. You can put it down below. You can put it down below to the left. You can put it down below to the right. Doesn't really matter. Wherever you put it, the same thing's going to happen to it, and you know what's going to happen. So 1, 2, 3. We're going to add chromic first. Then we'll add on the hypochlorite, and then we'll add on the Swern. Okay, so let's start with chromium. Chrome goes in, beep, that hydrogen off. That oxygen's attached to a carbon. And folks, this carbon is a secondary carbon. There's 2 carbons added onto it. So there is a 4th bond, and that 4th bond is a hydrogen there, just like always. Just because it's a ring doesn't mean that everything needs to change. Same deal, same concept. Beep, that hydrogen off, just like the other examples. And a double bond is formed between that carbon and that oxygen. If I go back and do hypochlorite, same product. Hydrogen removes, hydrogen here removes, a double bond is formed, I get the same thing. The Swern, hydrogen gets removed, that hydrogen gets removed, a double bond gets formed, and it's the same product. All 3 of these, yet again, give me the same product because in the chromic version, this only gives me something different when we have a primary alcohol. And this is not primary, this is secondary. So all 3 products are identical. All right, so finally, number 6 is a 1,4-butane diol. All right, so 1, 2, 3, 4. There's the 4 carbons. Diol means 2 alcohol groups. Okay, well, where are they? Well, they're on carbon number 1, and they're on carbon number 4. So there they are. Now, the very first thing that you're probably going to pick up, I hope, they're on the ends. These are primary alcohols. So here we are going to get different products depending on what we have. So in the first version, I'm going to start with chromic acid. So chromic acid is going to come in, beep, that hydrogen off, beep, that hydrogen off, and I still have an extra one here, right? And a double bond gets formed. Well, Chromic looks at this and says, I can do this again because look at me. I ate my spinach today. I'm Popeye. And then another oxygen squeezes into that carbon and the hydrogen. So we end up with a carboxylic acid, and it does the same thing over here on this end as well. So that hydrogen gets removed, that hydrogen gets removed, a double bond gets formed, and folks, an oxidation step happens again. So this is going to be the product for our chromic acid reagent. So it oxidizes to an aldehyde, and then because they're primaries, chromium does a very good job in this process, and it's very strong, and it will do it again. So that primary group converts to an aldehyde. That aldehyde then converts to a carboxylic acid, just like we've seen in some of our other examples. Now, number 2 and number 3, those reagents happen the same way. There's no difference in those reagents. So here I'm going to redraw our 1,4-butane diol again, and with the hypochlorite and with the Swern. Okay, so this carbon has a hydrogen, this carbon has a hydrogen. There's actually an extra one there, but I'm not going to draw it because guess what? Beep, that goes away, and beep, that one goes away. And we'll do the same thing over here on this side, and that helps me free up a double bond that forms between the carbon and the oxygen. So here, yet again, we end up with 2 carboxylic acid groups, and over on this side, we will end up with 2 aldehyde functional groups. So the hypochlorite and the Swern give me the aldehydes, and the chromium, here in this case the chromic acid, has given me a carboxylic acid, simply due to the fact that the alcohols here are primary, not secondary. All right, so that's the big differences between our oxidation reactions. And that kind of finishes up that section in your chapter. If you're following along and reading in the chapter in the textbook, you're going to see a section of oxidation, and this now kind of neatly, I hope, wraps up the oxidation reactions that we've discussed. All right, so now we are getting ready to venture off into the next section of the text. And we are going to turn our back finally on alcohols. We're not going to look at alcohol reactions anymore. We now need to go on. And when we go on, the next word in the title of the chapter is ether. So now we need to take a look at ethers, and we need to look at their reactions that they can do, and we need to be able to comfortably work with ethers and predict products. So before I go on to the next video, I at least want to talk about the functional group for an ether. So an ether was something that was presented in Chemistry 251. It should have been, at least. And these ethers have an oxygen that's sandwiched in between two carbons. So they're kind of in the middle. So instead of an OH group here, really, we're working with OR groups instead. That hydrogen has been replaced with maybe a longer carbon chain. We're still dealing with oxygen, which means that oxygen still has free pairs of electrons. That means that this is a slightly negative area of the molecule. It could behave as a nucleophile, possibly. We just don't know that. But the conditions of the reaction will determine that, or at least help me determine that. So very similar to alcohol groups here. And just like with alcohols, these ethers have to be protonated. How do we protonate them? We kind of do them just like we did with alcohols. If we add on a little hydrogen that's right there, and that hydrogen gives its electrons to something else, then this ether can become protonated. And that protonated ether now turns this thing into a very good leaving group. Up until that point, though, ethers are going to stay intact. That ether is going to connect those two carbons together and hold hands with them. But when we protonate it, we now disrupt that relationship. And that protonation turns this thing into a very good leaving group, and that group will end up leaving the molecule. Very similar to what alcohols did, right? When we talked about alcohols, we talked about oxygen having these free pairs. We talked about hydrogens that could be donated to the system. So these alcohols will grab the hydrogen, remove it, those electrons get shoved down, and this OH group turns into really a very good leaving group of water. So this HOH now turns into a good leaving group because it's been protonated, and this H with the ether also turns into a very good leaving group because it's protonated. Folks, this is the setup of the reactions for ethers that we're getting ready to discuss in the next video. So the idea here, it's very similar. If you can draw mechanisms for alcohol reactions, you should be able to draw mechanisms for ether reactions. The first steps of these, very similar to the alcohol set, and that's one of the reasons that they group them together in the same chapter, and we talk about them at the same time. So in the next video, we'll pick up from here. We'll review a little bit of ethers again, and we might go back and review some nomenclature. Depending on how long ago you've seen this, you might need to know how to name ethers. So we'll go through and do some nomenclature review, and we'll also go through and predict some products of these reactions as they happen. I'll see you then.